So I want to pull out one specific topic from the core processes material, and that deals with Mars' magnetic field. So we already talked about this a little bit in response in going over the quiz. This process of differentiation where, as protoplanets in the earliest solar system began assembling, you basically have all of these grains, chondrules and micrometeorites and so forth coalescing under the force of gravity, building up larger and larger objects that keep smashing into each other. That smashing together produces a lot of energy. A lot of kinetic energy gets converted into thermal energy. So at least in this respect, Lowell was correct in terms of the bodies in the solar system that eventually formed the Earth, Mars, Venus, and so forth, starting off as hot molten assemblages, especially for the interterrestrial planets. And we talked about this process of differentiation where the heavy stuff sinks to the center, the lighter stuff stays at the crust, and you get this breakdown into core, mantle, crust arrangement as the planets differentiate. You've probably seen a diagram similar to this in middle school or high school. Structure of the Earth with an inner and outer core, a mantle, crust. You all accept this, I assume, but how do we know this? No one's gone down 8,000 miles into the Earth to see what's in the crust. So how do we know that there's a core in the middle of the Earth?
Because of its magnetic field?
Okay, Earth does have a magnetic field, so we have to have some physical mechanism that's going to generate that.
We do like sonic imaging to figure out densities.
Yeah, but how do we do sonic imaging? It's not like we've got a big ultrasound machine. What do we use to do that sonic imaging?
Speakers.
Yeah, but what's generating the sound? Or the pressure waves? Earthquakes. Okay, so we've got seismic stations all around the Earth. When earthquakes happen at point X, off the coast of Tokyo, waking up Godzilla, then those pressure waves propagate through the crust, through the mantle, through the center of the Earth, and are detected at seismic stations all around the globe. And by timing how long those pressure waves take to get from the site of origin of the earthquake, we can tell how fast those pressure waves travel, and the density and properties of the material that it's traveling through is going to influence the speed at which those sound waves or pressure waves propagate. So that's the main way that we have to actually kind of X-ray or do a sonogram of the inside of the Earth. And it's clear that, if the earthquake happens here and it's being measured, over here in my Brazilian geography is bad. I don't know, Sao Paulo. Those waves would have traveled fairly superficially through the crust and travel at a speed characteristic of that material that it's going through. On the other hand, if there's a seismic station, up here in Oslo, Norway, that is measuring those waves, they would have gone more directly through the Earth and accessed these deeper layers of the planet. And again, by timing the speed at which the the speed at which the wave travels, as indicated by when they're detected by the different seismic stations, geophysicists can infer what kind of materials the waves are traveling through. So there's that. Seismic stations. The fact that we do have a global magnetic field leads us to suspect what about the core of the planet?
So how do we know what's going on with Mars?
Yeah, we don't have a bank of seismic stations on Mars, right? So what data can we get? We'll talk about that in a minute. You get a magnetic field generated when you have electrically charged material moving. And so you basically find global magnetic fields around planetary bodies if there is an underground salty ocean that can have tidal movement of salt water that can lead to an induced magnetic field. In the case of the Earth, we're talking about a liquid outer core of nickel and iron, which are good conductors of electricity. So it's essentially the dynamo, the movement of that material leads to the global magnetic field, which feeds back on itself to generate the moving electric currents. And this is essentially 19th century physics that is underlying the electric motor is essentially similar, related to the processes, the geophysical processes that are generating the global dipole magnetic field for the Earth. We also can do materials science. Can take different minerals and metals and in the lab expose them to temperatures and pressures that we would expect to occur in the center of the Earth and see, measure the properties of those materials in the lab. So it's a whole variety of lines of evidence that come together to allow us to reconstruct this picture of what's going on in the Earth. Now, how does Mars and how do Mars and the other terrestrial planets differ from the Earth? Clearly, we don't have as good a data for Mercury or Venus or Mars or that figure shows Ceres, which is the dwarf planet out in the asteroid belt. We know that Venus has no global magnetic field. We actually have found that Mercury has, even though it's so much smaller, has a somewhat of a global magnetic field. We know that Earth has a global magnetic field. There was a long time question mark about Mars. And I'll play a clip in just a minute that talks about that. But we can essentially tell the diameter of Mars, right, from our observations. We can also weigh Mars. We know how much Mars weighs from its gravitational influence on the moons that go around it. And if we have the weight of Mars and the volume of Mars, what are we able to calculate about Mars? The density of Mars. Okay, so we can calculate the density of Mars without having a geophysical station on Mars at all. So we'll have a lot better data once we get that InSight mission down on the surface of the planet, measuring earthquakes and heat flow and so forth. But we can measure the density. We can, as one of the articles talked about, carefully track the radio signals from the landers on the planet and very carefully look for wobbles or changes in rotational velocity, and that inertia to changes in movement can tell us also something about the distribution of mass within the planet. So we do know that Mars is differentiated into a core, mantle, and crust. If Mars was not differentiated, it would be spinning in a different way than it is currently spinning. We would have different behavior. Based on the bulk density, the weight, the diameter of the planet, how it's spinning, that moment of inertia, all of these things, geophysicists can generate models of what the interior of Mars is likely to be, and they can put some constraints. You can say, this kind of a core, it's still kind of a question whether there's any molten core if it's completely solid, with this range of diameters. If we had seismic stations on Mars, we'd be able to get this much more accurately. But even with this kind of remote data coming in, we can infer that Mars is differentiated into core, mantle, and crust. The core is somewhere within this size range. The mantle is somewhere in this thickness, and so forth. And we can refine those measurements as time goes on. Now, I do like this aspect of this diagram here, in that there is a fairly large question mark on the core. So we really, this is not my central area, but my reading of the field is that we're still unsure whether there is some amount of molten core or if it's all solidified. Why would Mars's core be more solidified than the Earth's?
Because the planet's cooler.
Planet's cooler, and why is it cooler?
It's older.
Not older. Earth and Mars are the same age.
Smaller.
It's smaller.
Yeah.
So it has lost heat relatively more quickly, surface to volume. Okay, this is important because the molten core on the Earth provides a magnetic field that protects us from the solar wind. This fairly ominously portrayed view of the solar wind here, blasting the Earth. It's not quite that dramatic if you're actually out in space, but we are much happier on the surface of the planet having a global magnetic field than we would be if we didn't have a global magnetic field.
What would be the ultimate consequences for planet Earth if the magnetic field were to disappear altogether?
5, 4, 3, 2, 1. We have ignition.
The answer has become clear only recently.
And we have liftoff of NASA's Mars Global Surveyor as America begins its journey back to the red planet.
In 1996, NASA sent a satellite to Mars.
Mars has been a difficult planet to get to with spacecraft. Even after 16 missions by US and Russia and so on, we still did not know whether Mars had an intrinsic magnetic field or not.
The Martian rocks.
It was this long-standing question which Mario Acuna and his team from NASA hoped finally to settle. What they actually uncovered was considerably more significant.
Nature had big surprises for us, beyond our wildest expectations.
Hidden in the history of Mars lay the connection between magnetism and life.
And here is where we develop our expensive toys, our instruments. This is our lab.
Mario is one of the world's leading experts on extraterrestrial magnetic fields. He has sent instruments to measure them all over the solar system.
This one went to Jupiter, Saturn, and beyond. This is Voyager 1 and 2. This one went to Mercury with Mariner 10. This one went around the orbit in the Sun. This one went to Comet Halley, for example.
To measure magnetic fields, Mario uses a technique which was discovered a century and a half ago.
The simplest way to measure a magnetic field is with a little magnet like we have here that has been mounted in such a way that it can move freely in 3 dimensions. And this magnet, because magnetic field is a force field, will align itself with the Earth magnetic field, in this case, in this direction that we have here, which is actually going into the core at an angle of 70 degrees here and pointing north. So that gives us an idea of the direction of the field. And you can see that if I perturb this magnet just slightly, how fast it recovers the original position gives us indication of the strength of the magnetic field. So it's very weak for the Earth, and if I use a strong permanent magnet, then we see that our test magnet moves much faster. So if I make this magnet work against a spring, I get an idea of not only the direction of the field, but also how strong it is.
In the Mars Global Surveyor satellite, the instruments are electronic rather than mechanical, but the principle remains the same. A tiny electromagnet which works against a magnetic spring.
So here's my spring, here's my magnet, and if I pass an electrical current through my spring and measure the disturbance of my magnet, which is inside, then I can transmit back to Earth the information about the strength and the direction of the field we are trying to measure.
As Mars Global Surveyor started to send back data, it soon became clear to Mario and the team that today Mars has no overall magnetic field. But the satellite also detected signs indicating that that had not always been the case.
We found these huge magnetic fields in the crust, and all of a sudden a completely unexpected and unknown planet, in a sense, emerged.
Although there was no magnetism coming from the core of Mars, strangely, large areas of the surface were strongly magnetic. The Martian crust is mainly made of frozen lava, a remnant of the time when Mars was covered with volcanoes. And there is a way volcanic rocks can get magnetized when they form. If molten rock cools in a strong magnetic field, iron-based minerals in it can pick up that magnetism, and the resulting solid rock will itself be magnetic. So, the fact that there was magnetism in the Martian crust proved that when the lava first erupted, Mars must have had a global magnetic field.
And not only that, at an intensity which is 20 to 30 times that of the Earth.
So that's basically similar to Earth.
Mario's team now knew that Mars had once had a magnetic shield, which it must at some point have lost.
Well, not most of them, but 30 or 40.
They began to wonder whether this might be the solution to one of the great mysteries of the solar system. Scientists suspect that the young Mars was in many ways an Earth-like place, with a thick atmosphere and oceans which may have harbored primitive life. But then, around 4 billion years ago, the planet entered a catastrophic decline. Gradually, the atmosphere and oceans of Mars mysteriously disappeared.
The puzzle was, where did the water go? What process could have caused the loss of water?
Mario realized that 2 dramatic events in the early history of Mars might lead him to the answer.
We found 2 very large impact basins in the southern hemisphere of Mars, which are Hellas and Argyre. There was absolutely no magnetization over them.
In these basins, formed when 2 huge meteorites hit Mars, the rocks were strikingly free of magnetism. And that was odd, because the huge impacts must have melted the crust. And as it cooled again, the rock should have become magnetized by the strong Martian magnetic field. Yet, there was no trace of magnetism in Hellas and Argyre.
Which immediately meant that they were formed after the magnetic field of Mars has ceased to exist. And the estimate is that these impacts took place more than 4 billion years ago.
4 billion years ago is when Mars was beginning to lose its water and atmosphere. Though not all scientists agree with him, Mario is convinced that the timing is not just a coincidence.
If we shut down the magnetic field, then the solar wind has direct access to the atmosphere of Mars. Then we have a process which is equivalent to the erosion in a desert. The wind blows and it blows the sand away. In this case, the sand are atmospheric particles. Slowly but surely, the atmospheric gases, which includes water, are carried away and are lost to Mars.
The loss of its magnetic shield could well have meant death for the red planet. Exposed to the wind of radiation from the sun, over millions of years, its atmosphere was gradually blown away, leaving the sterile world we see today.
If we were to turn off the Earth's magnetic field, the same process would occur. The atmosphere of Earth would be
Recording and okay, so what's the main question that Acuna and his team is addressing?
What would happen if Earth lost its magnetic field?
No, I mean that's the focus of the Nova
Okay.
show, but the researchers that they portrayed.
I'm not sure like at what stage we're talking about. Like I'd say why does Mars not have a magnetic field
Okay.
when it has evidence that it did have a magnetic
Right.
field?
So Jeff, what were you going to say? Okay, I mean the general question is, we don't know much about Mars' magnetic field. To some extent, this is just kind of exploration. If we send a magnetometer to Mars on the Mars Global Surveyor, what kind of a pattern will we see? Fundamental question is, does Mars have a global magnetic field or not? Why are we interested in that question?
Because if it does, the likelihood of life being able to survive on Mars increases greatly.
Right. I mean, we kind of like having our global magnetic field as surface-dwelling animals, and so, you know, we'd be interested to know if Mars has a global magnetic field. No, Leon.
Does the North Pole of Mars have snow in it?
Yeah, the poles are colder.
The poles have ices.
So it does have some sort of water on Mars, though.
Well, we'll talk about the poles in more detail when we get to that section, but there is a combination of carbon dioxide ice and water ice that make up the poles. Okay, so one big question is, does Mars have a global magnetic field? That was basically the main question that was to be asked. And the method for asking that question?
Flybys and magnets.
Okay, Mars Global Surveyor was not a flyby mission, it was an orbiter. But to send a magnetometer, an instrument that could actually, from orbit, measure the magnetic field and tell whether or not there's a global magnetic field like on the Earth. So the primary question is global magnetic field. The primary method involves sending an instrument that can remotely detect the magnetic fields. I mean, we have no, let me take that back. We don't obviously sense the Earth's magnetic field, although there is some evidence that humans do have some magnetoperception. But this is another example where the progress of science is really dependent upon our ability to develop more and more sophisticated instrumentation that allows us to collect data that would go beyond the kind of just raw observations we would be able to make if we were in a capsule going around Mars. Okay, and then the results. What were the main results? Global magnetic field? No. And what's your interpretation of that? Deadish. I'm not quite dead yet. Oh, shut up.
You to say that it's dead.
Okay, so no global magnetic field, no dipole global magnetic field, meaning that there are not sufficient processes going on in the core to generate this global field.
I thought what was interesting is kind of like using the crater dating that we did.
Mm-hmm.
They were able to figure out like when it probably disappeared. What did they say, 4 billion years?
Right. So before we get to that, though, the next step after asking and answering no, there's not a global magnetic field, what sort of magnetic fields did they see?
Remnants of a magnetized volcanic rock.
Right. So we've got these crustal fragments that are magnetic. It's kind of like a fossil magnetism. They are magnetized. So this is our interpretation of that is what? What do we interpret from the fact that some bits of Mars crust are magnetized?
It probably had one at one point.
It would have had to have a global magnetic field in the past for that crust to become magnetized when it formed. So no global magnetic field now, but our interpretation is that there must have been a global magnetic field in the past. So at some point in the past, Mars did have a global magnetic field, which is not unexpected. Early in its history, you might expect the core to be dynamic enough, to be molten enough to generate this magnetic field the way that the core on the Earth does. Now, getting to your point about dating, what's the refined observation that goes beyond this? I mean, where do we see the crustal, the magnetized pieces of crust? None in the northern hemisphere. The northern lowlands don't have any fossil remnant magnetism, and they're younger than the southern highlands. So the old southern highlands are where we see the remnants. But what was the deal about Hellas and Argyre basins?
There were no magnets inside them.
Okay. So Hellas and Argyre were not magnetized, which means at the time that they formed, what's your interpretation about the global magnetic field of Mars?
It was gone.
Must have been gone by then. Okay. Mars is how old? How old's the Earth? How old's the solar system? How old's the moon? 4.5 billion years old, 4.6 billion years old. And we think Hellas and Argyre were formed by relatively late impacts during the late heavy bombardment period of the early solar system formation, about 4 billion years ago. So just based on these observations that we can make today from orbit using the magnetometer and interpreting them, we can build a story that it's quite likely that Mars did have a global magnetic field when it was first created. We've got evidence in the rocks to tell us that. It doesn't have a magnetic field now, so it must have lost it at some point. And to the extent that we can date those basins through the crater counting and other techniques that we talked about, we can say by 4 billion years ago, Mars had already lost its global magnetic field.
So it only had the magnetic field for like 0.5 billion.
Half a billion years, 500 million years, and then it petered out. Now, the researcher goes on to associate that with the loss of Mars's volatiles, the air, atmosphere, and water, and so forth, with Mars being subjected to the solar wind without the protective shield that we have from our magnetic field. I mean, it's a reasonable argument that the solar wind could have stripped away atmosphere and water and caused Mars to dry out and lose its atmosphere compared to earlier. That's not universally accepted. I mean, to some extent that probably did occur, but we don't know to what extent the atmosphere of carbon dioxide and water actually are still remaining in reservoirs on Mars that aren't in the atmosphere. So the water could have gone to subsurface ice, and the carbon dioxide could have gone to carbon dioxide ice as the planet cooled off. We don't necessarily have to assume that all of that material was lost to space. I will mention that the latest mission by NASA to Mars, this MAVEN mission, is sent there specifically to measure how the solar wind is interacting with the current day atmosphere of Mars and how much Mars is still continually losing water, hydrogen, carbon dioxide being stripped away into space by the solar wind. So the results of the MAVEN mission may give us some better ideas about to what extent this loss of magnetic field might have been actually tied to Mars getting to be pretty crappy as a planet.
Look. Is that what I think it is?
Yeah. It's Mars. That's where they went.
Look. One stayed behind.
Earth, before the continents separated.
My God, that's it. Hundreds of millions of years ago, there was a sudden explosion of life on Earth. The first multi-celled plants and animals appeared. No one has ever understood why or how it happened. They seeded Earth.
They're us. We're them.
Okay, so no Lonnie, right? Let's first list some reasonable presentation of science in this clip. What did all, okay, Josh.
They're wearing spacesuits in space.
Okay. Somehow the atmosphere inside the structure is miraculously what they need so they can take their helmets off, but before they got there they were wearing spacesuits.
They show Mars being hit by a meteor.
Okay, so
Sense of the state that it was in.
giant impact. We do know that Mars has been pummeled.
Minus the whole alien part of creating Earth, they actually showed the evolution here.
Okay, so we'll talk about. They're trying obviously to incorporate some idea of evolution of life on Earth to carry forth their narrative. Colin?
Yeah, they showed the planets going around the sun.
Okay.
Everything going around it.
Okay, so they were in nice Keplerian elliptical orbits around the sun. The planets weren't exactly to scale.
Yeah.
Yeah, that was. It's not just the planets, but like the whole thing wasn't to scale. Like there should be a lot more space in between them.
Space is big. Space, there's a lot of
Space.
What else?
What else? Accurate things?
Yeah.
Well, they tried to show life on Earth with little animals.
Okay, so they're showing some diversity of life on Earth.
I don't know the term for this, but when like life comes outside of the planet, like enters a meteor.
They're drawing on panspermia.
Yeah.
Which is the idea that we the life on Earth might have. Well, they're not actually saying that life from Mars gave rise to life on Earth. They're something very more specific. Yeah. You had something? Okay. Bogus science.
The idea of the pre-Cambrian, like the Cambrian explosion being this like rapid thing that happens is kind of it's a misunderstanding of how fast it actually happened. It was millions of years that it went on for.
Okay.
But like when you hear Cambrian explosion, you think 1 second, bam,
Yeah.
everything starts.
Yeah, there was indeed something called the Cambrian explosion in the fossil record, where this big diversification of life. We'll talk about how that relates to this panspermia thing. There's too many hands. There. Yeah, or can humanoid aliens.
Were they talking?
He understood.
Yeah, there wasn't really any talking, but the fact that the alien was, yeah, someone who hasn't. Go ahead.
Meteorite impact wiping out all the water and landscape.
Okay, we'll talk about that. Yeah.
The fact that the aliens were able to anticipate this explosion and then be able to get off the planet, save themselves.
The alien exodus.
Can't say anything about the aliens, right? We don't know. They couldn't be fast enough to just get off.
500 million years would not be enough time for life to develop, for evolution to create beings of that,
Advanced life so early.
Advancement, and then have them get to this technological level of being able to leave the atmosphere and go to, the far reaches of the galaxy.
In the back.
They were like walking to gravity, seemed like
Oh, okay. When the astronauts are walking in what I call the planetarium, it's okay.
Can you just add that on that list, the planetarium?
Josh.
We're Martians.
We are Martians. I'm going to put that over here.
That's hilarious.
Because.
We are Martians? Did you get the thumbnail?
That's still an open question.
The worst question.
We know that there is constant interchange between Earth and Mars of material. We know that Mars could have been habitable for life earlier than the Earth. So going back to Lowell, Percival Lowell, his idea that Mars might have been habitable earlier than the Earth, there is some basis to that. And, if anything, it's more likely for life on Earth to have derived from life on Mars than vice versa, because it's easier to get stuff from Mars to the Earth than vice versa.
Like the planetarium and stuff, like, we put that on a false list, but, I mean, who's to say that, like, advanced life didn't develop that fast? Sure, like, all we know is a planet in our form of life, but...
Right. We are, one of the other courses I teach is Search for Life in the Universe, astrobiology. And we are very much hampered in terms of our investigations into biology on Earth here, because we have essentially one data point. As far as we know, all life on Earth is related, shares the same common molecular genetics and cellular structures and so forth. And we know on the Earth it took close to 4 billion years to develop beyond single-celled organisms, and it took 4.5 billion years until just recently for us to develop any sort of advanced technology.
So 500 million years is still like, it's not impossible, but it's incredibly statistically improbable.
Based on our one data point, we would say yes. Yes.
But that's also like a bad.
It's very. I think it's a very arrogant point of view.
It's certainly.
We're working with the data we have, and the data says.
It's certainly very anthropocentric. It's very terrocentric, very Earth-centered.
Very small sample size.
Yeah, very small sample size. Other things people want to bring up.
They're able to breathe on Mars.
Well, they're inside. So clearly the aliens thought 4 billion years into the future, when humans might be coming to Mars from the Earth, let's create this face on Mars structure so that they have some place to come to.
Well, I mean, in theory, the idea that there's oxygen inside there is not that big of a jump to make, because we're assuming that the aliens breathe oxygen as well.
Yeah.
We're assuming they breathe oxygen as well because of the Earth before, Mars before every stuff went down. So it wouldn't be a large jump to assume that they also breathe oxygen, and that's why it's there. But
yeah, you're going to run an advanced metabolism, high energy being. It's nice to have some oxygen around. Colin.
When the aliens sent stuff to Earth, they sent DNA, and DNA does not just magically create an organism by itself.
Right.
I think that whole the thing of I think that was
symbolic.
Just more symbolism.
Yeah, symbolic, yeah.
I'm assuming they sent cells down there.
Yeah, you can't. There are situations where naked DNA will be taken up by cells and become incorporated into the genetic machinery.
No cells to begin with.
The idea of, as portrayed in the movie, this was a way of jump-starting the Cambrian explosion. So we already had life on Earth for 3 billion years at that point, but all single-celled kind of stuff. Okay. So yeah, there's kind of a patina or a veneer of science that they're trying to make use of. Do you think that what they were representing in this clip was the impact, for example, that created Hellas Basin? Hellas Basin is the largest identifiable basin on Mars right now.
Well, wouldn't there not have been any of that life on Mars when that was created because the poles were already gone by then?
Not the poles, but the magnetic field.
The magnetic field, yeah.
Right.
Gone,
so I think that's one misconception. It's not that the Hellas Basin impact did away with the magnetic field. The magnetic field had already collapsed before Hellas Basin. Now, we'll get to in a minute, there is more recent works that suggest that some of the earlier larger impacts that were so large that they don't even show up as a basin anymore might have actually shut down the magnetic field of Mars. So if it's Hellas Basin they're depicting, no, it's wrong because the magnetic field was already gone before Hellas Basin. But if they're trying to depict one of these earlier mega impacts that might have shut down the magnetic field, maybe so. The whole panspermia thing is a little strange because, well, and actually before we even get to that, an impact of that size, based on what I saw for the impactor coming in, would have probably turned the surface of Mars into a molten sea. A molten sea of lava. I don't care what technology you have. You're not going to escape the planet with that kind of an impact, unless you leave before the impact.
Wouldn't that like impact? It wouldn't be that destructive. It would be like the dinosaurs kind of.
Well, it's an issue of scale.
Yeah, you can't really tell the scale from the planetarium is not to scale,
right.
So
Yeah.
I mean, any mention of scale goes out the window.
The impactor that killed off the dinosaurs.
5 miles across, right?
Yeah, and if you were seeing that coming in versus the diameter of the Earth, it would have been this little pinprick dot coming in. So anything that was large enough to show up in this scene as the impactor would have been a huge mega planet killer kind of impact.
Would have been like another small planet.
Yeah.
Coming in kamikaze.
Assume that there are advanced aliens and they have spaceships and they can get off after the impact. Looks like they're going to the center of the Milky Way.
It looks like they're going to what?
To the center of our galaxy, right? Why is everybody heading off a gazillion miles away when there's Earth next door?
There's Earth next door, or they could go to Venus. Like, there's much better options.
Probably head to the black hole.
Yeah, but why? That's a terrible option.
They'll be teleported into space.
They're aware that Earth can harbor life. They were the ones that started. Why didn't they go there?
Now, when was the Cambrian explosion? Somebody probably knows.
Wait, say that again?
Cambrian explosion.
What about it?
When?
When? It was
500 to 600 million years ago.
Yeah.
560 million years ago.
Wouldn't that have been after the continents split up?
Yeah, the whole phrase about Earth before the continents split. Well, the continents have come back and forth together many
The
times.
continents never really split up.
Yeah.
They were never really together.
When did Mars lose its magnetic field?
4 billion.
More than 4 billion years ago. Cambrian explosion was maybe 500 million years ago. So these aliens are so advanced they can fly to the center of the Milky Way, but it takes them 3.5 billion years for a spacecraft to get from Mars to Earth to see the Cambrian explosion.
They only had 500 million years to develop that technology.
They lost it.
Yeah.
That's the opening pitch.
And then the presentation of evolution. What do you think of that?
It's really weird.
It was
It's what you can do with CGI, right?
It was kind of painful to watch.
Yeah.
It was kind of painful to watch.
It's very linear and very progressive, and that's a common misunderstanding about how evolution works. But
It was very fast.
it was very fast. But, I mean, clearly we don't have organisms transmutating from one to another that way. We don't have a linear progression of life. You know, evolution is this diversification and extinction and kind of life fumbling around and adapting to different kinds of environments. And, you know, the idea that, you know, the goal of evolution was to produce humans is fairly deeply ingrained, even among people who accept the evidence for evolution. But it's really a very strange way of thinking about how evolution actually works. Is there a? I thought I saw a hand over there. Okay. So, like I say, I'm still waiting for a good Mars movie, but I think it's interesting to look at those situations where sciencey topics are presented in things in popular culture, like Mission to Mars, or Red Planet is another movie that came out the same time as Mission to Mars with Val Kilmer in it.
Did you see Interstellar?
Yes.
I thought that was really interesting how they tried to incorporate string theory.
Yeah, well, they actually had a very famous cosmologist as advisor on the movie, so that helps.
I just want to say the whole Mission to Mars thing. A lot of the stuff they showed there could have been avoided if they made it another planet that wasn't Mars.
Yeah.
Like, I think a lot of the problems come from trying to fit it to Mars because there's a very limited time scale to work with.
Yeah.
And then we know a lot more about Mars than like.
You could have just made up a planet in the galaxy, say.
Well, if you look at science fiction and speculative fiction and future histories and things, that all those genres of fiction, whether you're talking about text or movie or whatever. There's been an interesting progression in that space as we have learned more and more about Mars. It's become less of a venue for that kind of speculative fiction. I won't go into detail in this last slide because we need to get on to other matters today, but essentially, how and why the magnetic field of Mars collapsed is still an open question. It very possibly could have just been Mars cooled down more quickly, the core cooled off more quickly. We still, maybe once we get the InSight mission or some other geophysical stations on Mars, we'll have a better idea of what the current status of the core is, to what extent there's a molten core versus a solid core. But, clearly Mars lost its global magnetic field 4 billion years ago, either because the core just ran down and cooled off, or it's possible that some of these mega impacts basically disrupted the heat balance between core, mantle, and crust in such a way that basically shut off the dynamo and would have led to the loss of the magnetic field. We are getting better at projecting back further and further to find evidence or patterns that relate to what these large mega impacts might have been in the past. So, hopefully this is an area that will also get some clarity in the next decade. Okay, so currently, as we've talked about, Mars has no global magnetic field. It's got these magnetized areas of crust. There are, and you can't see it very well unless we kill all the lights. There are some of these areas of crust are strong enough to provide a little bit of an umbrella of magnetic field to deflect the solar wind. But basically, much of Mars is just open to the solar wind and the effects of that.